Welcome to part P of chapter 9, our lecture. This is part P. In part A, we covered section 9.1 through section 9.4. Part P, we will look at section 9.5, hybrid orbitals, 9.6 multiple bonds, that's double bond, triple bond, and then molecular orbital, and we will look at the second part of or second theory in chemical bonding. Remember, there are two theories as far as the formation of covalent bonds are. In part A, we looked at the valence bond theory, where it is postulated that, or we know that the formation of covalent bond is as a result of overlap of atomic orbital. In part P, we will look at the formation of molecular orbital using the quantum theory, which we looked at before in the atomic structure in chapter 6, atomic structure of atoms, where we are right now, the quantum mechanical model of an atom. In section 9.8, we look at the bonding in period 2 and the atomic molecules. Let's see, in 9.5, we'll still extend the use of valence-shell electron pair repulsion model, see how hybrid orbitals are formed. So far, we know valence-shell electron pair repulsion models predict the shape of the molecules very well using the APX, EN, where A stands for the central atom, BX, external atoms bonded to the central atom, and EN for lone pairs of electron around the central atom. We use that model to predict the shape. But how does it now fit to atomic orbital? For example, how are the bonds formed in H2O, for example? If you look at the electronic structure or electron configuration for oxygen, there are 4 electrons in the 2p orbitals. We will expect to form 90 degrees, but it is the bond angle in H2O is 104Y. This turns out that when oxygen and hydrogen bond, there are some new orbital form we call a hybrid orbital, which is formed by mixing atomic orbitals to create new one we call degenerate. Degenerate orbitals means they have the same energy. The process by which, atomic orbitals are mixed together to generate new degenerate orbitals is called hybridization. Let me demonstrate to you how the mixing takes place. For example, in CH4, all right, we know carbon, excuse me, has 4 lone pairs, which means it can form 4 bonds. And then I meant to say CH4 here. And let's say we have 4 hydrogens, right? 4 hydrogens with each single bond. If you look at the electron configuration for hydrogen, it's 1s2, 2s2, 2p4. That's electron configuration for what? Electron configuration of carbon. With what? With 2 NS, the ISN the highest energy level being 2. The orbital filling diagram, let's see, 1s, 2s, then 2p here. Remember, we have 3 orbitals in 2p subshell. We have 2 orbitals in 2p subshell. So here is 2p. If we write the electron configuration using up and down arrow to show electrons, this is carbon is number 6. It has 6 electrons. So far we have 1, 2, 3, 4. So we have here 1, 2, 3, 4, 5, 6. So we have 6 electrons and 2 unpaired. All right. So here are 2 unpaired electrons, 2 unpaired electrons. The question is, how will, all right, how will the 4 hydrogens form chemical bond with only 2 unpaired? Remember, we need to pair electron to form carbon. This is now where hybridization comes in. This is where hybridization comes in, that is the mixing of orbital. We need to hybridize. There is a need to hybridize this. That means we need to generate and degenerate orbitals for these 4 hydrogens to bond with carbon. And hybridization is promoting of 1 electron. So if this is carbon right here, 1s, 2s, and 2p here. All right, 2p here. We will promote 1 electron. All right, we will promote 1 electron from the 2s here. You see this? And then we add our own electrons here. We still have 6. 1, 2, 3, 4, 5, 6. So here are the hybrid. These are now a hybrid. All right, hybrid orbitals, hybrid orbitals. So hybrid orbitals, and it's now available to form the chemical bonding with hydrogen. This is hydrogen, this is hydrogen, this is hydrogen. Hybridization is the mixing of orbitals to generate. So when 2 orbitals mix, we end up with 2 hybrid orbitals. When 3 orbitals, atomic orbitals mix, we end up with 3 hybrid orbitals. Remember how many orbitals when they say the number of orbitals, the number of atomic orbitals being hybridized generate equals number of hybrid orbitals, atomic orbitals. When we say sp, there is sp, sp2, sp3, sp3d, sp3d2. It's the number of or the orbitals being mixed to get the degenerate. For example, beryllium, and when we talk about hybridization, it's done on the here node. Understand this hybridization or hybridization is done on the central. So we cannot do the hybridization on, mostly hybridization is done on the central atom. Recall the central atom from the Lewis structure of molecules or polyatomic ions. So when you see this PE, it stands for beryllium being the central atom. And in all other hybridization, we will hybridize the central atom, and you should be able to recognize central atom in a molecule. One or two, number of hybrid atomic orbital being mixed. So in other words, if you have two hybrid, if you have two atomic orbitals, you'll end up with two hybrid orbitals. If you have three atomic orbitals, you'll end up with three, and so on. You see this? This is what thing you need to understand as far as hybridization. We only do hybridization on the central atom. Here, what do we mean by PE hybridization? It means beryllium. This is the chemical element on the periodic table, and if it is central atom, we have sp hybridization. Beryllium, this is electron configuration for electrons. And if you look at the orbital filling diagram, we do not have lone electron to form a chemical bond. There is no electron available for bonding. Therefore, we do what we call hybridization, which is promoting one electron to 2p sublevel, all right, which will leave us with two unpaired electron available for bonding, So here, hybridization has been done. We call this sp hybridization, sp. Just leave that. These are degenerate orbitals. We call it sp. It's not an s by itself, and it's not a p by itself, but it is sp hybrid. There is a general equation which I want you to learn, commit to your memory, so that it will help you in determining the hybridization on the central atom. And this is the equation. Let me just write this. I want to title this as formula determining I wanted to show you. Let me just minimize this so that you see the whiteboard. So the formula for determining hybridization. All right, here, hybridization on the central atom, And this is given by H for hybridization equals to 1/2. I'm going to explain what this means. Okay. I'm going to explain this in a minute. H plus V for valence electron plus M for monoatomic minus cation plus anion. This is an equation you need to learn, you need to memorize. What stands for H, of course, stands for hybridization. H stands for hybridization, and V stands for valence electron. So let's break it down here. H equals to M equals to C equals to, and then A equals to. H stands for hybridization, all right? And M is monovalent, and C is for cation, and C is for anion. I think you should know what is meant by cation right now. I believe you know what a cation is, anything with a positive charge. All right, and this when we refer to anion, negative charge. I'll demonstrate this and back to hybridization. The first two is probably what you need to know, or okay. Hybridization is either sp3, which we're going to look at once we do practice with this. Monovalent, let's see. Monovalent. It is a species which can donate or share one electron in covalent bond. So any species which can donate one electron, all right, is regarded as monovalent. E.g., hydrogen is monovalent. It got one electron. Fluorine, anything on group 7. And remember, we are looking at the molecules, and these are non-metals, non-metals, so that this is also monovalent. It can, you see, it has only one unpaired electron, and fluorine has one unpaired electron. We call this monovalent. Now, divalent, which we are not going to look at, has two. Or two unpaired electrons. Trivalent, e.g., or rather, before we look at trivalent, example here, e.g., oxygen, sulfur. For example, if you look at this 1, 2, 3, 4, 5, 6, we have two unshared electron. We say divalent. Likewise for sulfur, 1, 2, 3, 4, 5, 6. It has two unshared for di. Now for trivalent, all right, trivalent, just to explain what that means. This means 3 and shared electrons. Nitrogen, if you look at nitrogen, it has 3 unshared electron. We call it trivalent. The reason why I'm bringing this so that we know what monovalent is. Monovalent in this equation means it has one unshared electron, and this has to be on the external atom. Right here, external, it got to be external atoms. All right. Cation or anion, are you dealing with polyatomic ion? Are you dealing with a neutral molecule? If it is polyatomic cation, you'll indicate the charge on the cation. If it is +1, such as ammonia, polyatomic cation, or hydronium, polyatomic ion, they have a charge of +1. If it is anion, either you are dealing with sulfate, for example, has a charge of -2, phosphate has a charge of -3. Okay, will indicate the charge. We cannot have a cation and anion at the same time. All right, it's either cation or it's either anion. So that in this equation, you can either have a 0 for cation if it is anion. If it is anion, then this will be 0. So whatever we'll plug in here in this equation, in order to determine the hybridization, all right, hybridization, you indicate the charge for the cation, charge for the anion. If you are dealing with anion, that means cation will be 0. If you are dealing with the cation, A will be 0. Monoatomic, you know how many monoatomic external atom do you have? And then V for valence electron. Here, V, all right, V, I forget to show you V. This stands for valence electron. For the element, for valence electron for central atom or the atom in question which you are hybridizing. Remember this equation we are going to use to determine the hybridization of the central atom. I don't want you to just you know, use the table and memorize the table, but using the equation, if you like the equation, that's fine. If you want to memorize the table, that's fine too. But I find the equation more straightforward. It's easier to remember, and I may give you in the exam or quiz so that you use this one to determine the hybridization. I'll work a couple of examples to show you how this equation is used to determine the hybridization. For example, in beryllium, do you need to, or you don't need to memorize this slide in order to know that beryllium is sp2 hybridization. For example, you know, when we talk about sp, that means we are mixing a p orbital with an s orbital to end up with an hybrid orbital. Well, let's see, in beryllium fluoride, right? Beryllium is the central atom attached to fluorine. We use this equation, all right? If we use the equation, we will have a hybridization. That means a half of valence electron for beryllium. Beryllium is in group 2, so that means it is 2 plus monovalent is, we have 2 monovalent right here. Look at this, mono, right here, M equals to mono valent, all right. Monovalent. In this case, we have 2 fluorine. Therefore, we have 2 there, 2 fluorines, minus 0. It's a neutral molecule, BeF2. It's not a cation. Plus 0. It's not an anion either, which means a half of 4 is 2. What does these 2 stand for? This is where you need to remember when hybridization is 2, all right? These indicate how many orbitals are hybridized. In this case, if here, if H is 2, 3, 4, 5, 6. If you end up with a numerical value of 2, 3, 4, 5, 2, 3, 4, 5, the hybridization here is, you need to learn this. This is sp, sp2, sp3, 3, sp3d, sp3d2. You need to remember this to reproduce to help you in knowing the hybridization. So we'll have to determine the value here using the equation here. We'll have to use this equation, which I have learned here. You need to know what these values are. H for hybridization half. This is valence electron on the central atom using the main group element, for example, using the group number on the periodic table, of which in most part you'll be dealing with main group element, not the transition, not the inner transition. So it's easier to figure out the valence electron. Monoatomic, remember these are the atoms on the external atoms with only one unshared electron. We include how many they are. If it is divalent, as I explained, you do not include. We do not include trivalent, and this is cations. What is the overall charge of the cation? What is the overall charge of the anion? And then here, once you get the numerical value for H, you reconcile with the hybridization. If the numerical value for H is 2, then it is sp hybridization. If H is 3, then hybridization is sp2. If H is 4, hybridization on the central atom is sp3. If H is 5, then hybridization on the central atom is sp3d. And then if H is 6, and then hybridization on the central atom is sp3d2. sp3d2. So for beryllium fluoride, we did our mass, and the value for H here is 2. We make a conclusion, or our conclusion is that the hybridization on beryllium is sp here, based on the look at the whiteboard. If H is 2, which we did for beryllium, hybridization is sp2. This is the easiest, this is the quick way of finding the hybrid or determining the hybridization on the central atom, okay? Hybridization. sp2, all right, put on sp2. How do we know? You don't need to memorize. Let's see if we use the equation to determine, for example, sp3. I mean, hybridization of sulfur in sulfur trioxide. You don't need to memorize what is in the text, or maybe pulling off the internet and saying, oh, this is hybridization of sulfur trioxide, sulfur dioxide, or methane CH4. Don't memorize. All you have to know is plug in this equation. H equals to 1/2 into valence electron plus monoatomic minus cation plus anion, and see how many hybrid orbitals you have. So for S3, SO3, 1/2, sulfur is in group 6, so it is 6 minus 0. Why 0? Because oxygen, this is a divalent, which means it has two unshared electron. What I mean by divalent, we are looking for monovalent, which we don't have it in this molecule. We just say 0 minus 0. It's not a cation. There is no overall charge or positive in this structure. Plus 0, because we don't have what? We don't have a positive, negative charge. It's not positive, it's not negative. If it was an overall charge of -2, we will add 2. If it was overall charge of +1, and then we will subtract 1. So this is 1/2 times 6 equals to 3. And from this right here, look, 3 is sp2. So I know, therefore, S in SO3 sp2 hybridized. sp2 hybridized because of 3, H is 3 in this case. So that's what I'll do, or I want you to learn, practice with it. Even end of chapter problems, this equation will work. This equation will work. All you have to know is what does phi stand for, what does M stand for, C stand for cation or anion. It will help you in determining the hybridization. For carbon, okay, in methane CH4, with carbon at the center, it is sp3 hybridized. Means we are hybridizing 3p orbitals and an s, a total of 4 s, 1 s, 3, and we end up with 4 hybrid orbitals. 1, 2, 3, 4. 4 hybrid orbitals for sp3. sp3 hybridization, this is CH4, so we put in, for example, H2O. Hybridization. Oxygen has 2 bonds and 2 lone pairs, resulting in sp3 hybridization. For hypervalent means atoms with an expanded octet rule. Elements that have more than octet, it can take more than 8, means you can have 10 electron on the central atom. This is because of the d orbitals. Remember, d sublevel can take a maximum of 10 electrons. 10 electrons. And those molecules with, or hypervalent molecules, are those molecules with that central atom being on 3rd row on the periodic table and below. We will not look in details into those, but we'll just limit ourselves to row 2 to see how the hybridization is done in such a way that you end up, or you generate degenerate orbitals for chemical bond formation. You know, you need to draw the Lewis structure, use the valence shell electron pair repulsion to determine that, or use the equation instead of following the guidelines here, which summarize that. So examples given here for molecules with either sp2, sp3, sp4, or I mean sp3, sp2, I wouldn't really recommend memorizing examples of given molecule. You don't need to memorize. All you have to know is that equation I gave you, which will help you in figuring out the hybridization on the central atom. You may be asked to find the bond angle. Okay, for sp it is 120, sp3 109. Okay, so let's see. Given the hybridization, or give the hybridization for oxygen in OF2. We will use this for OF2 like that. For OF2 like that, H equals to 1/2 valence electron plus monovalent minus cation plus anion. Close the parenthesis. We are looking for the hybridization on what? On oxygen. Oxygen is central. So this will be 1/2 into valence electron is 6, oxygen is into 6, plus monovalent. We have 2. Monovalent fluorine has Fluorine has 2 unshared electrons. This is the equation I'm using to predict the hybridization of oxygen in OF. This is the equation 1/2 into valence electron for oxygen 6 plus 2, 2 monovalent. If it was something else other than an atom with only one, we will ignore. Let's say, for example, oxygen is divalent, just 2 unshared electron. It is a neutral molecule, so this will be 0 and plus 0, 0. Cation, no. Is it anion? No. So 0, 0. This is a half of 8, which is 4. 4 sp3 hybridized. It says sp3 what? sp3 hybridized from this equation here. Is 4 hybrid orbitals, and they are s and p3. sp3, the correct answer is B for this. So so far I want you to go back. I use that equation to predict hybridization on the central atom using end of chapter problem. Should also work for homework problems, predicting the hybridization on the central atom. Let's shift gears to 9.6 multiple bonds. When you say multiple bonds, these represent the double bond and the triple bond. Remember, double bond right here, double bond is 2 lines, and triple bond, these are just 3 lines. 3 lines. When we talk about the multiple bonds, how do we hybridize double bond and triple bond? There are 2 types of bonds. Sigma, here, sigma, we call this sigma. And it's just, you may relate to this when we say single bond, it has only 1 line. Sigma bond is always a single bond. And then pi bond here, call this pi bond. Gonna have this here. Pi bond. Just double. It has 2 lines, 2 lines. These are the types of bonds which sigma bond is just characterized by head-to-head overlap, but side-to-side leads to sideway overlap. Sigma bond and pi bond, side-to-side, side-to-side overlap, or head-to-head for sigma bonds. Depending on the type of bond you have, for a double bond, double has 1 sigma and 1 what? 1 pi bond. This would constitute a double bond. From here, if you look at the double bond, pi bond, there is an overlap. All right, there is an overlap for pi bond, carbon to carbon, double bond. So double bond consists of 1 sigma and 1. So here are 2 pi bonds and 1 sigma for multiple form. All bonds are pi bonds. Gonna have that localized. So that's what I want you to know as far as double bond. Let's see triple bond. Triple bond here. Triple bond is 1 sigma and 2 pi bonds. 2 pi bonds. In pi bonds, there are some delocalized. That means the electrons are not only confined to one atom in the molecule, but can be delocalized. That means they can move around. This explains why some molecule fluoresce. We do not, or we see electrons moving within atoms, such as in benzene. There's some delocalized electrons. Well, that's what I want you to know as far as the double bond is concerned. What constitutes a double bond, sigma bond, 2 sigma bonds, 1 pi bond. Let's see the molecular orbital theory, how a molecule or how the bonds are formed in a molecule. Molecular orbital theory, we have looked at the valence bond theory. Molecular orbital theory, we will use the quantum, all right? We will use the quantum mechanical model of the atoms, all right, to explain the chemical or molecular bonding. Molecular orbitals, remember we have the atomic orbitals and molecular orbitals. Molecular orbitals have many characteristics like atomic orbital. This is an atom, this is an atom. When they combine, they form a molecule. Molecular orbital have a maximum of 2 electrons per orbital. All right, these are properties of MO, molecular orbital. It can just take a maximum of 2 electrons, just like atomic orbital. Electrons in the same orbital have opposite spin. When you write up and down arrow, they have opposite spin. They also divide energy. We can visualize the electron density by the contour of the diagram. There'll be a diagram I want you to memorize. So what's the difference between molecular orbital and atomic orbital? Molecular orbitals represent the entire molecule. This means it does not look at each of the atom in the molecule, but just look at the whole molecule in a whole. Whenever 2 atoms, right, overlap, 2 molecular orbitals are formed. And these are bonding and antibonding. Bonding at the bottom and the bonding at the top with more energy. And the bonding orbitals are always destructive. That means they are not favorable. They have few features. We will not get in details on the nodal planes and stuff like that, but I want us to see how the molecular orbitals are constructed and how they are occupied by electrons. They are occupied by electrons in a given molecule. Here is molecular orbital diagram, which I want you to learn. Here in this case, we are using the atomic orbitals, such as in H2. What you see here is hydrogen gas. Hydrogen gas is H2. This is hydrogen gas with 2 hydrogens. This is atomic orbital. So if I have here 1s and 1s, each with 1 hydrogen. These are atomic orbital. They can combine to form what we call molecular orbital. And the electron from each, right, electron from each atom form or occupy the lowest. We call this sigma star 1s. This is sigma, this is just sigma 1s. The lower one is antibonding. You always remember this is antibonding 1s, sigma s. One thing you need to know is you write the electron configuration going up and then write the electron configuration going up. This is 4H2, and when they mix together, they form molecular orbital. Here we call here molecular orbital. These are right here. These are right here, molecular orbital. Molecular orbital. So what you see in the middle here is molecular, and each electron here is coming from each oxygen. Each oxygen. One thing I want to label or you need to know is the top part, these are antibonding orbitals. These are bonding orbitals. We use these to calculate what we call bond order, or to tell us how many bonds are formed. And bond order, all right, bond order is determined, maybe I can just summarize by saying bond order equals to 1/2 bonding, or rather number of bonding electrons minus number of the bonding electrons. So bonding minus half of bonding electrons minus number of antibonding give the bond order. And for hydrogen gas, 1/2 into number of bonding electron. We have bonding electron, 2 bonding electron minus 0. There is no electron here. And we have one bond order of 1, which we know hydrogen gas, or hydrogen molecule rather, has 1 bond. Was 1 bond. Hydrogen has 1 bond. You will need to draw the molecular orbital diagram in order to determine the bond order. Otherwise, it's going to be hard for you to figure out the bond order unless you see clearly the bonding electron, the non-bonding electron, count the number of bonding electrons, and that will give you the bond order. Using He2, that is helium, just showing as if helium is diatomic, it turns out that there is no bond, which means there is no molecule such as E2. If we plug in this equation, this is atomic orbital for helium. Helium has 2 electrons, and we assume that we have our diatomic helium. Bonding electron here, 1, 2, that's where the 2 comes from, minus the 2 and the bonding here, 4 or 0. We don't have anything, which means there is no bond between helium to helium. You will never see, what that means is you will never see something like this H bonded to H. We don't have, it's not going to react. It's not going to react. That's how to use the bonding or molecular, using molecular orbitals to determine the bond order in a molecule. Now, for section 9.8, bonding in period 2, bonding in period 2 diatomic molecules, these are the guiding principles for formation of molecular orbitals, or simply formation of MO. When you say MOs, these are molecular orbitals. AOs stand for atomic orbitals, which I had stated earlier on. Guiding principle number 1, the number of molecular orbitals formed is equal to the number of atomic orbitals combined, all right? So if you have this one atom with its atomic orbitals, and you have the other atom with its own atomic orbitals, when you combine that, it should give you equal number of molecular orbitals. Let me go back to previous slide. 1 plus 1, we have 2, so we end up with 2 molecular orbitals from atomic orbital. That's all about guiding principle number 1. Number 2, atomic orbitals combine with atomic orbitals of similar energy levels. So you'll not have, atomic orbitals with different energies. It won't work. The effectiveness with which 2 atomic orbitals combine is proportional to overlap. Okay. Just the way we wrote the electron configuration of element, we follow Pauli's exclusion principle. You will not have a parallel atom. I mean parallel electrons with parallel spin. That's Pauli's exclusion principle. For example, here you will not have same spin pointing up. Will be violating Pauli's exclusion principle. That when they occupy, when electrons occupy molecular orbitals, they should have opposite spin. So when molecular orbitals of same energy are populated, one electron enters each orbital spin before pairing them up. We call those degenerate orbitals. So here is the molecular bonding for lithium Li2, which has been proved to exist in the lab based on the bond order, all right? This and this will cancel out. And if I want to find the bond order for this, bond order for Li2 is going to be, it's given by a half. Bonding electrons, this and this will cancel out, so it's going to be 2 minus 0, and then we end up with 1. So there's a bond order of 1, which we know Li2 really exists. Where the 2 is coming from, this and this will cancel out. All we have to account is the outermost shell, which is 2. The 2 we have here, we don't have any antibonding electron. We don't have antibonding electron. You need to learn how to draw the diagram here, and it's going to change depending on which element you are looking at. Molecular orbital diagram for second period, the p block element on the second period, not row 3. All right. There are sigma and sigma star orbitals. The star means antibonding, by the way. There are pi and pi star overlap for p orbitals. All right, so if I have a 2s, these are sigma bonds, bonding and the bonding. Now for 2p, this is the arrangement of molecular orbital. If you look at the atomic orbital, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is how molecular orbitals are arranged, and the electron will occupy from the lowest to the highest energy level. I saw that there is a difference between oxygen, or there's difference between oxygen gas, fluorine gas, neon gas, when it comes to second row beryllium or boron, carbon, and nitrogen, group 2, oxygen, fluorine, and neon, they are in group 2. There's some interaction between 2. So if I look at the bond order for beryllium is 2, and the reason being bonding minus and the bonding is half of 2 is 1, half of 4 is 2, half of 6. So you end up with the bond order for each one of them. A half minus 2 minus 0, we don't have antibonding. Do you end up with 3, for example? 2s, 2p, or bonding here, we have 6. Half of 6 is 0. We don't have anything up there. You don't have anything up there for that. So that's how you sign the, or you determine the bond order. Bonding minus and the bonding. How do we end up with 2 here? If I look at the bonding, bond order of 2, 1, 2, 3, 4. 4 minus 2 is, all right, 1, 2, 3, 4 minus, or here 2p, 1, 2, 3, 4, 5, 6. So 6 for oxygen here. Just minimize this. How do we end up with a bond order of 3? Bond order is given by 1/2. 3 is because of 6 into 6 minus 0. We don't have antibonding here. No antibonding electrons, so the bond order is 3. We use the molecular orbital diagram also to indicate or state whether a molecule is paramagnetic or diamagnetic. Paramagnetic means it is attracted towards the magnet. When you place in a magnetic field, it's attracted towards the magnet. Diamagnetic means it's not, or it will not be attracted towards the terminal of a magnet. Paramagnetic, that means it has magnetic properties, has lone pairs of electrons. That means for diamagnetic, all electrons are paired up. For example, in the first compound, beryllium or boron, P2, there is 2 unshared electrons, 2 unpaired electrons. In this case, we say it's paramagnetic. Diamagnetic because all are what? All are paired up. So unless you write down the molecular orbital diagram and fill it in, you will not be in a position to tell whether it is paramagnetic or diamagnetic. I don't want you to just memorize and say this is going to be diamagnetic or paramagnetic, but you need to write the molecular orbital filling diagram. I will try maybe use carbon, for example, show you why it is diamagnetic. Why it is diamagnetic. So if I write the carbon here, let's say carbon and carbon. Carbon is number 6, so 1s, 2s. Then we have another one here. This is 1s, 2s, and then 2p. What I'm doing here is writing electron configuration, and this has 1, 2, 3, 4, 5, or 6. I'm gonna do the same thing here. 1, 2, then 3, 4, 5, 6. So this will combine to form 2. Likewise for this, combined with that, this will now form the 3. You look at the 3 here, there is an overlap. There is an overlap with the 2 and 1, with the 2 and 1. There is a 2 for carbon, 2, 2, 2, 2. So if we put a 2 here, this is 1, 2, 1, 2. What I'm looking is I'm putting the 2 electrons, these 2 and these 2 gives us 4 here. The 2 and the 2 goes there, and then here, all right, they will give us the 2 here for carbon, 2s. So we have a 2s. The 2s here will just for carbon 2, 2. And there is the pairing for 1, 2, 3, 4, 5, 6. 6. So you have here 2, you have here 2, or 1, 2, 3, 4, 5, 6. So pairing up here, 1, 2, gonna have the pairing them up there. So all of them they are pair up in carbon as shown here. So you don't see here you don't see in diagram here, this is molecular orbital, but I'm showing you that the atomic orbital for one carbon, atomic orbital for carbon on that side, with pairing them so that when all of them are paired up, we say that it is a diamagnetic. The one with unpaired gives us the molecular the one with the paired will be paramagnetic. We say paramagnetic. Now for the highest energy level occupied by these, unless you draw the Lewis structure for molecular orbital for that, you'll end up with 2 pi. The correct answer for this is 2 pi. You need to see for fluorine to fluorine. This is F2, by the way. This is just F2. And if I go back to F2 here, the highest occupied, look at the highest occupied energy level. These are the molecular orbital, and the highest occupied is 2 pi star for fluorine. For nitrogen, based on the molecular, the bond order for nitrogen to nitrogen, I'll still draw that nitrogen to nitrogen. I don't see antibonding. So for nitrogen, if I minimize this right here, for N2, bond order is given by 1/2, 6 minus 0. This is a half times 6, which is 3. We have a bond order of 3. It means can form 3. Zero antibonding because we don't have what? We don't have antibonding or electrons in the star. Electron in the star stands for antibonding. If we had electrons here, and then we will subtract that based on that. So the correct answer is C. The correct answer is D. I've explained earlier on what is meant by paramagnetic. Diamagnetic molecules are those molecules with unpaired electrons, all right? The substance with paired electrons, if all of them are paired, we say diamagnetic. Paramagnetism is a shallow presence of one or more unpaired. Oxygen, for example, if you look at oxygen here, we have two unpaired, we say it's paramagnetic. This is diamagnetic unpaired. This is, no, this one, you know, we don't have tone order, all right? Diamagnetic, paramagnetic because of unpaired electron. So unless you draw the molecular or write down the molecular orbital diagram to predict whether it is magnetic or diamagnetic, it's going to be hard for you. So draw the molecular orbital diagram to determine which one of the following is paramagnetic. Without really drawing, I'm just going to use this table here to show you which one or how to eliminate. If I look at O2 negative, that means we have to extrovert. We have two extra electrons. So for two extra electrons for oxygen, that's going to pair them up here. It's going to make it diamagnetic. For two negative, we'll add two more electrons. It will make it magnetic. So A is wrong. If we add or remove two electrons from here, we remove two electrons, still gonna be paired up, making it a diamagnetic. O2 positive, that means we remove two electrons here, right? We remove two electrons from this oxygen here. That means it's just gonna remain with paramagnetic, and the answer is D. It will be paramagnetic. Why would we say D is paramagnetic? F2E plus, that means we remove two electrons. If I remove two electrons from here, that means either these two electrons, two of them will be unpaired, making it paramagnetic. It's just demonstrating the paramagnetic properties of oxygen, which illustrates that they are attracted towards, oxygen are attracted towards the magnetic field, right? You can do the same thing for heteronuclear. Heteronuclear means molecules or molecular orbitals for different atoms. Hetero, look at this, nitrogen and oxygen. Previously, we looked at homonuclear, heteronuclear. The atomic molecule consists of atom or consisting of atoms from different elements are said to be heteronuclear. They may not really have the same energy because of different, okay, but still the bonding follows the same as the homonuclear, except that the energy level are not the same. I want you to read more. Chapter 9 homework assignment should be available. Hopefully, we will not have any major update or maintenance on the website, just the way we had this past weekend. Other than that, the quiz will be posted. Please continue studying and make sure that you complete the online homework before the due date. Thank you.